let's take a look at this probability problem. Suppose we draw one card from a standard deck, which is shown here. Let event A be drawing a red card and event B be drawing a king. What is the probability we get a red card or a king? So I want to look at this in a couple different ways. Now, you may have seen a formula, let's write this down, that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Now these formulas can get a little confusing, and so I really want you to understand why this formula is working. And I think the easiest way to do that is not use the formula at first, but really just look at these two events separately and see what's going on. All right, so let's look at event A, drawing a red card. So we're just drawing one card. All right, what's the probability that I draw a red card? Well, shoot, let's look at it here. All right, these are the red cards. So if I just think about the probability of drawing a red card, there are 26 outcomes in my sample space. I have 52 outcomes in my sample space of drawing one card. There's 52 possibilities, and 26 of them are drawing a red card. So the probability of just drawing a red card is half, right? 26 out of 52. All right, let's look at the second event. So the second event is drawing a king. Okay, well, let's just look at that. What's the probability I draw a king? So here's my kings right here. So there's 4 of those. So the probability of drawing a king, which is event B, is 4 out of 52, which reduces down to 1 out of 13. All right, so you might say, well, if I want to do the probability of drawing a red card or a king, then I'm just going to add those together. But hopefully you see the problem here. If we actually just look at the sample space and count the number of outcomes that have a red card or a king, we wouldn't count these twice, right? We could count, okay, there's 13 plus 13, and then these two more, that's 13 plus 13 plus 2 is 26, 27, 28. I really don't have to use a formula at all, right? If I can visualize the sample space and just count the number of outcomes, I would get 28 out of 52, which would reduce down. Let's see if we divide by 2. We could probably divide by 4, huh? Divide by 2, divide by 2, divide by 2, divide by 2. I would get that. If we would have just counted the number of red cards, which was 26, plus the number of kings, which is 4, and said, oh, there's 30 outcomes, and then divide that by 52, we would have got the wrong answer. Well, why is that? Well, the issue is we would have counted these two outcomes right here twice, right? There's only one card there. So that's this business right here. That's what this business is in the formula. All right, so the probability of A is, well, let's just put it in terms of 52. Okay, so 26 out of 52 are red, and 4 out of 52 are kings, but I counted 2 of those 52 cards twice. So I need to subtract them out, and that's why this formula has this subtraction part. Now, if the two outcomes are mutually exclusive, in other words, they don't share any outcomes, there's no overlap if I highlight my outcomes, then this is 0. If they're mutually exclusive. In this case, they are not mutually exclusive because they share 2 outcomes. All right, so if we finish up with this formula here, we get 26 plus 4 is 30 minus 2 is 28. Lo and behold, we get the same thing we did here when we were just looking at the sample space and considering all the outcomes that were red or king. So hopefully that helps you understand why you have to subtract out this and piece and what visually is happening with that and piece of the formula.